Not for the recording. Okay, good morning, everybody. Welcome to the second session, morning session of the second day of VMCAI'. My name is Borzubon Aktarpur. I'm from Michigan State University. I'll be chairing this session. The first talk is multivariable quantification of BDDs in external memory using nested sweeping. And the talk is given by Steffan Sølvsten.
Thank you very much. I thank all of you for also all the way over here. So science is said to be built on the shoulders of giants. And this little project is absolutely no different in that. For the first, I would actually like to start to go back all the way to 1986, where Randy Bryant published this paper, which until quite recently actually was the most cited paper in all of computer science, until the AI wave took over and then tons of citations then. And what the thing Randy did was say there's this idea of a binary decision diagram, where you have a tree where nodes are merged like this. And every node here is then an if then else decision on some Boolean variable. So here we x0, if it's false, we go down here. If this variable is true, we go down here. And at the very bottom, we then also have all of these, the output of this Boolean function. So this is one way to represent Boolean formulae. And the idea that Randy had, building on top of this original definition by Lee and Akers, was to say, what if we have these variables occur in a specific order? So in this picture, it's always x0, then x1, then x2, and then x3. First of all, what we get out of that is, with a few extra tweaks in here and there, that this actually is going to be a canonical description of the Boolean formula. So if no matter how you write this Boolean formula, if it is functionally equivalent to another one, the BDDs will be structurally the same. So equality checking of Boolean formulae are very much trivial with binary decision diagrams. Another nice thing that comes out of having the ordering be fixed this way is that the algorithms themselves are very simple and to implement and to actually also analyze. And this gives us then also some really nice complexities in terms of the performance of this thing. So if you have a formula phi and some formula psi, and you want to compute the and, the or of this whole thing, you can do that purely in the time that is based on the size of the BDD, not actually the complexity of the formula. So you might have a very complex formula, but the BDD is teeny tiny, and because of that, your computation runs really fast. Of course, the BDD can also explode, become exponentially big, but, well, yeah, then you have troubles. But still, next to that, you can also assign a variable a single Boolean value that will also be an operation that will only depend on the size of the BDD, not actually the complexity of your formula. If you combine these things, you can also do the existential quantification, because that is essentially just the same as assigning false, assigning true, and doing the or of these two. And because combining these two things, we then also can do that in quadratic time, based on the size of the BDD. Now, this was really big back in the 90s. Then SAT solvers came in, kind of took all of the glory, with very good reason. They are doing a really good job with that. But there are still some use cases where binary decision diagrams are useful, both from just regular model checking, but probabilistic model checking still sees very heavy use of BDDs nowadays. Quantum is on the rise, and analyzing quantum algorithms on a regular machine, binary decision diagrams are kind of finding their way to as a representation of the matrices. And also they're finding their way as the explainability of AI algorithms nowadays. So they kind of like also have a resurgence this way. But the usual way you're implementing this is by doing recursion. This is a nice recursive structure. Let's not redo computations all the time, so let's do some memorization. So that's a hash map. Let's not recreate the same nodes several times. So let's also have another hash map for that. So hash maps, and recursion. That's a lot of jumping around in memory, which isn't really the best in terms of how our computers actually work. So if we go all the way forward or backwards to 1996, Lars Age just finished his PhD in Aarhus, and began to look at one of the first things he wanted to look at in terms of I/O, later finding lots of other places where he had a high impact on the design of practical and theoretical algorithms for with respect to like optimizing how the I/Os work. Let me try rephrase that. So he ended up being a very big person within the area of I/O efficiency. I/O efficiency is the idea of trying to make an algorithm that actually has optimal reads and writes on the data. And so one of the first few things that he actually began looking at was binary decision diagrams and how can we actually optimize the behavior of these. And one of the things he proved was if you use depth-first recursion and you use memorization tables, you will asymptotically, in theory, have bad behavior. And you can also see that in practice nowadays. There was a paper relatively recently by Pastva and Hensinger, which essentially proved that our CPUs are getting faster, but they're also getting faster compared to the RAM. So the RAM is now slower compared to the CPU. So actually, the speed of BDDs are actually slowing down nowadays compared to the CPU time, because we are not actually properly dealing with cache misses. But he also proposed a different way of actually computing on binary decision diagrams. So what he proposed was to say, what if we have this BDD operation? It could be the AND, the OR, the exist. Let's split it up in two different parts. First, we have the apply phase, and then we have the reduce phase. So if we want to do an existential quantification, we have one formula and one variable as an input. We're going to have some transposed output into between, and then we're going to be cleaning up a few things afterwards. The way this kind of then looks is if we have a BDD like this. Let's quantify out the first variable here, x1 variable, sorry. And so we're going to be doing this by going through the whole thing, sweeping level by level. And so slowly we build by level the output. X1 would then be turned into an OR node, and then we continue the computation all the way down like this until we have final output. What is interesting about this way of doing it is, first of all, how is the input laid out in memory? We make sure that it actually is laid out level by level, so meaning that we have, by having computed it this way, we've also been following the order in which the input was laid out in memory. So we've just been sequentially reading through the input, and sequentially reading through the input is I/O efficient, so that's great. But how did we then actually deal with all of these recursions? Because these recursions were also jumping around inside of memory. So instead of using a stack to deal with the recursions, we're going to be using a priority queue instead. And this priority queue is then taking your recursions and then sorting them to match the order in which you're going to be reading the input. And so essentially what you have here on the right is the recursion tree unfolded into a diagram like this. And the priority queue also actually is able to merge recursions to the same target together. So it also is doing double duty as the memorization cache. So if anyone was worried about this exploding in this thing in between, this tree is the same size as you would do the one you would be traversing in your normal recursion, except for the fact that you're now actually outputting the whole thing. But as you can also see here on the lower right, we're also creating some nodes that need to be reduced. Essentially, at this point, we have been simulating the recursion down, but we haven't been simulating the return of the recursion at this point. So that's going to be the next step, the reduce. So we're going to start from the bottom. Luckily, some of you might have noticed these edges were already reversed. That was, let's not go into much detail, but that was because the way we outputted the whole thing previously, nicely everything then just ended up being transposed, which is lucky for us because we need to know the parents to actually return to them. So again, reading through the whole thing sequentially, which is just running through the output backwards. That's the same as going back up again. We can then also have a priority queue sending information to our parents. And so we end up creating the final output. This is essentially all you need to know about how these algorithms worked. Everything else is magic. So how does this look how is the complexity of this thing then? Well, similar to before, we might have a formula phi and psi. We want to compute the AND and the OR of this. And now we have this kind of looking the same thing, but slightly different. So it's the sort of these two formulae. So it's the sorting complexity, which usually in the time is like going from n to n log n. So we add a logarithmic factor on top of it. But in the I/O model, the sorting is also an n log n thingy, but random access is exponential. So it is some way heavy improvement, going from exponential down to an n log n. So we're paying a little bit of a cost asymptotically in the running time, but we're gaining a lot in the I/O complexity instead. You can also apply the same idea to then assign a variable, a single value. Again, you get an n log n kind of thing, but have a heavy improvement on the I/Os. And combining this again, you can also do quantification of a single variable by combining these two steps into a single algorithm, again for quadratic complexity with a small logarithm on top of it. And if you can quantify one variable, you can also quantify k variables. Every time it might grow twice as large and double in size, so you kind of get this exponential increase in the size, which is also equivalent to what you're seeing in the asymptotic complexity of the depth first version. So it is essentially running asymptotically as we would hope for in most cases. So if we now go all the way over to 2022, I, together with a few others, we dusted off this paper by Lars Age and actually implemented it in practice in a tool called Adiar, which, given all of these algorithms and building on top of a library that actually implements I/O-efficient priority queues, I/O-efficient reading and writing of files, and sorting algorithms, gives you the ability to actually compute on binary decision diagrams that are way, way larger than the RAM of your machine. So we ran, and also we're later going to be seeing benchmarks, algorithms running on a computer with like 300-ish gigabytes of memory. And we were dealing with binary decision diagrams of 700, 800, 900 gigabytes in memory, or gigabytes in size. And the performance was essentially not changed. It was as fast as the smaller ones. You didn't pay the cost of going to the disk, whereas if you're going to use a recursive implementation, you're going to be using swap memory, and then you're going to have several orders of magnitude performance decrease. So for large binary decision diagram manipulation, this will work really nicely. But until now, at least, we've always been quantifying. If we what I've showed you previously was essentially also the way we're doing it in here, not the original way that Lars Age actually proposed to do it. He did it a little bit more complex because he was mainly just interested in the asymptotic complexity. So in part of this work was also just cleaning the whole thing up, simplifying it, optimizing it, making it run faster, and also both on paper and in practice, mainly in practice, not asymptotically. But at this point, we've only been quantifying one variable at a time. And so that kind of sounds like something that would be really bad if we want to do model checking and things like that. And usually the way that conventional depth-first ways of implementing binary decision diagrams do it is by actually having a nested recursion inside of the algorithm. So question is, can we somehow recreate the same thing in our implementation? If we want to quantify multiple variables, can we somehow have a nested operation so we're not dealing with creating stuff and touching stuff that we don't need to do? So that brings us to this year with this paper, where we then are proposing the idea of using nested sweeping. So if we take this previous picture with the reduce, apply, reduce tandem we had, we're going to wrap it in a second apply, reduce. So first of all, we have one apply phase, which just is going to do some computation. We can try and alter this a little bit, but it actually doesn't matter what this one is going to be doing. Let's just simplify things and just assume this doesn't do anything except reversing the edges back up again. So we know the parents. So we're essentially just transposing the input. But by transposing the input, we can start from the bottom and go up. So we get as the second animation you saw. And so part of the reduce, we now know all of the variables we want to quantify. So we're going back up until we find some variable we want to quantify. We're not touching anything above this, so we are skipping some work here. And now we're going to start a nested apply reduce phase down here until we're back up here, and now we can continue. Which kind of, again, now is the idea is that this simulates the way that the conventional depth-first implementations also would go down recurse and do something nested down here and then return. So the animation would then look a little bit like this. On the input on the left, I've already kind of transposed the inputs. So the edges point upwards. And now we're going to be creating this output here over on the right. Since this is already fully reduced, there's nothing really that happens. There's nothing much interesting going on in the beginning. We're just recreating the input essentially. But we can also do something else interesting on the input prior to that, but let's again ignore that. But at some point, we're going to get up to one variable we want to quantify. In this example, I want to quantify x0 and x1. And so now we want to do a nested OR operation on this forest I have beneath. So let's here in the middle actually do a nested operation on this entire forest, starting from the edges we have from the input that goes down into the original forest and also in here. So, and recording on the output also how this connects back, into the original input. So we go down, and similar to what you saw in the animation you saw previously, we're going to create this intermediate output where this node needs to be removed. And so now this output, this whole thing has done its work. We can just delete that file from the disk, and we create a new output. So, and now again, we can then go back up again with that, create the reduced output this way. And now this essentially, while going up here, we are overlaying this on top of that one to create the new version of the thing that we need to have reduced. And these gray edges are then used to connect this new version back into the original one. So we're going all the way back up here. X0 is also a variable we want to quantify, so that one is also going to, again, be seen as an OR node and spawning recursions for going back down again. So let's, again, remove the thing in the middle. We don't need that one anymore. And then start here again and going back down. We create the product of these two variables, nodes, and then also this x3 node, and then also the leaves at the end. Reducing this one is not that interesting. It's already kind of reduced. And so we have the final output. Asymptotically speaking, did we win anything? No. So still, if you have a formula and you have k variables you want to quantify, it's still going to be taking this exponential possible time. But that is also just because the binary decision diagram might explode. So there's asymptotically not any win. But as I mentioned previously, we're going up to some level, and then we're doing some work down here, never touching anything above. So we would assume at least that there should be some performance increase in practice, similar to why you're doing this whole thing, also kind of doing this whole thing in the conventional implementations. Yes, I'm good on time. So let's actually look at things in practice. For that, we have two benchmarks. First of all, we have a Garden of Eden question of, like, given a grid of size n1 by n2, in this case in Conway's game of life, does there actually exist some initial state that doesn't have a predecessor? So is this a initial state that is not reachable in any different way? So this is a problem that is very close to being a relational product, but without you wanting to use the relational product. So that is really nice in our case, because we want to test the existential quantification without having to deal suddenly with tons of different extra issues of how can we do something with the relational product. Next up, we have also tried out with quantified Boolean formulae. So you're given a formula with some exist for all and so on, with the quantifiers alternating until we find some matrix, some formula that depends on these variables. And specifically for inputs, QBF formulae that we're going to be using are like two-player encodings of two-player games, like Hex and the like, based from Scheik and Van de Poel. The reason we're going to be taking these in particular is because, based on our experience, these symbolic encodings actually work really well for binary decision diagrams. So this is a reasonable use case for actually using this data structure. So in orange, Garden of Eden, in blue, quantified Boolean formulae. So first of all, how well do we actually improve performance of our implementation? if you ignore these few dots here that are 5% performance decrease, in general, just the bigger things get, the more we get out of this. On average, we got an performance increase of like factor 1.7. I should have mentioned, yeah. So here on the x-axis, sorry. Here on the x-axis, we have the running time without the nested sweeping. And on the y-axis, you have the speed up gain. Sorry about that. So above the line would be speed up, and below the line, slow down. Okay. Next time, axis first. Let's talk about the axis first. Next up, we wanted to compare with another BDD package called CAL, back from the 90s, which is the only other BDD package, as far as we know at least, that tried to actually do binary decision diagrams on the disk. The way they did it was still using hash tables, then a hash table for every level, and then the breadth-first algorithms to try and be a better dealing with that. And the IOs to the disk was just dealt with by swap memory using the operating system. And here there's a kind of an interesting thing happening over here on the left, but let's start with the things on the right. So essentially, we are just winning by several orders of magnitude. Here on the x-axis, you have the running time for our algorithm, so the complexity of the whole thing. On the y-axis, you have the relative running time of CAL. And we are, in many cases, like several orders of magnitude, like 1,000 times faster than CAL. Pretty much all the way across the board. You have some X's on this plot. This is literally just because we underestimated how slow CAL was going to be compared to us. And for every instance, we had to actually note down how much time this specific instance was going to get, because if we gave everything 15 days, the scheduler would not be happy about us. So we had to somehow gauge how much it would be. So all of these X's are worse than their placement. Then you might be wondering about what is happening over here. CAL is actually kind of cheating. So for smaller instances, it actually uses depth-first recursion. And as far as we can tell, this is probably pretty much right around here that it actually is switching over from the depth-first recursion to the breadth-first algorithms. So at least in terms of like actually using the disk, we are at least right now it seems to be the fastest implementation. So that's also the goal. So that's really nice. But what about how well do we do against depth-first implementations, the ones you would actually usually be using? First of all, these benchmarks are run on computers with 300 gigabytes of memory. This is primarily just to make the depth-first implementations able to survive for long enough, and because we don't want them to actually throttle on memory in any way. And we've also set up a lot of different other settings in these things in their favor. So just to be sure before I show anything to you, we are essentially giving them every other implementation as much benefit as possible, except for the fact that the multi-threaded versions are also only given a single core. But other than that, it's very much in their favor. So we have in the paper, we have compared with 5 different implementations. Here I've just taken 2 that you probably would know. So Buddy from Copenhagen and CODD from Colorado. And Buddy has probably the clearest picture of how performance essentially goes when you want to compare. So again, below 1 second, we have an interesting area where the performance of our priority queues and reading and writing actual BDDs, tiny BDDs to files on the disk is just a major overhead, and you shouldn't do that. And so we are several orders of magnitude slower than this implementation, which is fair enough. It's out of our scope. It's not what we're trying to do, at least right now. And then, but at some point, at least our priority queue and files kind of stabilize on the overhead. And we stabilize around a factor of 4 performance slowdown of using Adiar over a depth-first recursion. But again, remember, like we have been given as much favor to the depth-first recursions implementations. So this is very much like a worst-case performance decrease, hopefully. But then at some point, after having been through these small instances, these medium instances, then we get to the large instances. And here, Buddy is suddenly just crashing in performance. And this is because it's running out of memory. It does so quite early because it only uses 32-bit integers. But because it runs out of memory, it tries to do garbage collection, and that is slow by itself. But also garbage collecting is going to clear out the memorization hash tables, which means that it's going to recompute on previous operations already. So it's both doing slow garbage collection and suddenly now recomputing quite a few things. And so suddenly it spikes in performance until it just completely gives out either with a memory out or a timeout. Timeout essentially just being, it's repeatedly garbage collecting, so essentially the same thing. And for CODD, it's kind of the same picture, but a bit more muddy. At least for things that are for small BDDs, we are completely crashing in terms of performance, but at some point it kind of stabilizes, and we are winning for larger instances. And with that, we can kind of say that with nested sweeping, we have been able to actually take these results we had from 2022, where we had also had a 4-factor decrease in performance, and we've been able to translate it over to these more complex operations like the existential and the quantification. So in general, this is just a framework you can actually apply to simulate any BDD algorithm that recurses more than just once. So you can do quantification. We also have the relational product since then implemented. You can also use this for functional composition. And if someone is interested, my PhD thesis is also providing you a pretty novel way of doing variable reordering based on this approach. All of which should be able to actually deal with binary decision diagrams way larger than the RAM of your machine. It also, having nested sweeping and supporting multi-recursion that way, also kind of gives you the ability to implement and support other types of decision diagrams, such as decision diagrams for quantum and for cryptography. And all of this just dealing with binary decision diagrams that otherwise is completely beyond the memory capabilities of your machine. Thank you.
Okay, we have time for a couple of quick questions.
Thank you for the talk. I would like to know, did you use solid-state drives or regular disk-butter hard drives for the evaluation?
The evaluation was on an SSD, yes. So it was only 100 times decrease in performance if you were using swap memory for the depth first implementations rather than a factor of 1,000, roughly speaking.
And do you think the algorithm would be highly impacted by having disk-butter drives with just sequential read, or would it scale nicely?
You can do a few things to make it scale more nicely, but yes, you're going to be slightly impacted by the disk. But I'm also would emphasize slightly. So maybe you would have a factor of 2 decrease rather than a factor of 10 or factor of 100 decrease in performance. Also, the way, not going too much into the I/O model, but the idea is instead of just reading a single page or something, you're reading in a bigger block of memory. By default, that block size is set to 2 megabytes. You could increase that to 16 megabytes, and by that you're also you're more dealing with or bridging this gap of problems. Reading from a hard disk, the expensive part is not reading the thing; it's seeking the thing. So the bigger things you are reading, the better it is.
Okay, thank you.
Yeah, thank you for the talk. I was wondering, your algorithm always goes to disk, right? So yes. No matter how small the BDD. So intuitively, I would assume that maybe the sweeping-based approach is even better also in RAM because it utilizes the cache better, like in comparison to the recursive approach. Do you have an idea if this is true? Like if you stay totally in RAM but still replace recursion by the sweeping?
I have not tried to say, I mean, the whole thing has been set up quite modularly, so you could do that, but I haven't done that. But you could try and see if you could replace files with internal memory vectors and replace the priority queue with a cache optimized internal memory priority queue. Then you would probably get quite a bit of a performance increase, yes. But I have no practical evaluation to back it up.
Okay, thank you.
Okay, I do have one question, but I'll ask you after the session in the interest of time. Okay, let's thank Steffan again one more time.